Howdy. In today's video, we will be doing DC analysis on two MOSFET transistor circuits. The first circuit we will be solving is shown on the left, where we have R1 is equal to R2 is equal to 200 kiloohms. RD is equal to 10 kiloohms. VTH is equal to 0.6 volts, and K prime W over L is equal to 3 milliamps per volt squared. We are being asked to first find the region of operation of the MOS transistor M1 if VDD is equal to 5 volts. So let me go ahead and write 5 volts right here. And so on the right, I have how to determine the region of operation. So this is taken from the MOSFET region of operation slides. So in order to determine the region of operation, we first need to determine whether VG is less than VTH, because that will mean we are in the cutoff region. So we know our VTH value is 0.6 volts, so we need to find our VGS value. And so let me write right here, this is our source, this is our drain, and this is our gate. Right? So VGS is the potential difference between point G and point S. As you can see in this circuit, S is connected to ground. So that means that our VGS is equal to VG. Right? Because normally it would be VGS is equal to VG minus VS, but our VS is 0 volts. Okay, so what is our VG value? We can find our VG value by doing a voltage divider. So we know that our VG is equal to R2 divided by R1 plus R2 times VDD. Right? Our VDD is 5 volts, our R2 is 200 kiloohms, and our R1 is 200 kiloohms. So this becomes 200 divided by 400 times 5, which is 2.5. You can also figure this out by knowing that R1 and R2 are equal resistances, so our VG value must be half of our VD value. And I'll write that equation because that will be useful for later. So our VG is equal to 1/2 VDD. In this case, it is equal to 2.5 volts. Right, and since our VGS, which is 2.5 volts, is greater than our VTH, which is 0.6 volts, this means that we are not in the cutoff region, right, because VGS is greater, not less than VTH. Okay, next, let's determine if we are in the active region. So we already know that our VGS is greater than VTH. Now we have to determine whether VDS is greater than VGS minus VTH. So we need to determine whether our VDS is greater than VGS minus VTH. And our VGS is 2.5 and our VTH is 0.6. Okay, so we need to find VDS, which again, VDS is equal to VD because our VS value is connected to ground, so that is 0. So how do we find VD? Well, if we look at our circuit, we can see that our VD value is equal to our VDD value minus the voltage drop across this resistor RD. So let me write that. VD is equal to VDD minus the voltage drop across RD. And the voltage drop across RD can be rewritten as ID times RD using Ohm's law. Okay, so now we need to find our ID value. And so using this slide, again, we are going to assume we are in the active region because that is what we are trying to figure out. So that means we are going to use the active region current equation right here to find ID. This means that ID is equal to 1/2 Now, UNCOX is equal to K prime right here. That's just a shorthand way of writing this. So I'm going to write 1 over 2 K prime times W over L times VGS minus VTH squared. Okay, and we actually have computed all of these values. So we know that our ID is 1 over 2. Our K prime W over L is 3 milliamps per volt squared. Our VGS is 2.5, and our VTH is 0.6 squared. Okay, now let me type this into a calculator. And we get 2.5 minus 0.6. We're going to square that, and we're going to multiply this by 3 over 2. And we get 5.415. Remember, this is in milliamps. Because our K prime W over L value is in milliamps. So that's what our ID is equal to. Okay, from ID we can use this equation right here, the VDD minus IDRD, to solve for VD. So let's go ahead and plug that value in. So our VD is equal to, our VDD is 5 volts minus, so 5.415 milliamps times 10,000 ohms gets us 54.15 volts. Now our VD value is going to be negative 49 volts, which is clearly much less than our 2.5 minus 0.6 volts. Right? It doesn't even make sense to have a negative voltage in this case. So we are clearly not in the active region, and therefore we are in the triode region. Okay, so we are in the triode region. Okay, let's take a look at part B, which asks, find the drain current ID if VDD is 5 volts. Okay, so since we are in the triode region, we have to use this current equation now, which is ID is equal to K prime W divided by L of VGS minus VTH times VDS minus 1 over 2 VDS squared. Okay? And we have everything we need to solve for ID. Now we need to solve for VDS. But remember, we already did that. Our VDS is equal to VD, which is equal to VDD minus IDRD. Right? That is the equation that we solve for right here. Right? Our supply voltage minus the voltage across this resistor, RD. Okay, so now we can make this substitution into our top equation, and let me rewrite this as ID is equal to K prime W over L VGS minus VTH times VDD minus IDRD minus 1 over 2 VDD minus IDRD squared. All I did was I just made this equation substitution for VDS. And we know that our K prime W over L is 3 milliamps per volt squared. Our VGS is 2.5 volts. Our VTH is 0.6. Our VDD is 5 volts. We know our RD is 10 kiloohms minus 1/2. Again, our VDD is 5 volts minus ID times 10 kiloohms squared. And that is equal to ID. Now we have one equation and we're trying to calculate ID, which is one unknown. And so you could type this into any algebra calculator and it should give you the results. And in this case, we actually get two solutions. However, one of them is positive and one of them is negative. So our two solutions are 0.491 milliamps and negative 0.651 milliamps. However, it doesn't make sense to have a negative current in this case, as a current needs to flow from the supply voltage to ground. So therefore our answer is 0.491 milliamps for part B. Moving on to part C, we are being asked, what is the current if we change our supply voltage to 1.8 volts? Let me go ahead and erase this and change it to 1.8 volts. Now, again, in order to figure this calculation out, we have to start back from the top. So let me go ahead and erase this as well. Alright, so now we need to determine whether VGS is greater than VTH. So because our VDD is 1.8 volts, we need to recalculate our G value. Fortunately, we can use the same logic as before, as if these two resistances are equal, R1 and R2, that means that we drop half the voltage at this midpoint right here. So if our supply voltage is 1.8 volts, our VG will be equal to 0.9 volts. And let me write this real quick. VDD is equal to 2 VG. And therefore, if our VDD is equal to 1.8, our VG value will be equal to 0.9 volts. Okay. And so our VGS value is equal to 0.9 volts, which is greater than our VTH value, which is 0.6 volts. And therefore, we are not in the cutoff region. Okay, next we have to determine if we are in the saturation region. And in order to do that, we have to find our VDS value right here. So we can use the same equation as before, which is VD is equal to VDD minus the voltage drop across the resistor, ID RD. And that means we have to solve for I. So we're going to use the active region equation for I again, which is I is equal to 1 over 2 K prime W divided by L VGS minus VTH squared. And this is ID. So that means our ID is equal to 1 over 2 times 3 milliamps per volt squared times our VGS value is, our VGS value is 0.9 volts. Our VTH value is 0.6 volts. If we square that, okay, let's recalculate our current. Okay, let's recalculate our current. So we have 0.9 minus 0.6 squared times 3 milliamps divided by 2, and we get 0.135 milliamps. Okay, from this, we'll be using our VD equation here to solve for our VD value. So VD is equal to VDD, which in this case is 1.8 volts, minus our ID, which is 0.135 milliamps, times our RD value, which is 10 kiloohms. Okay, let me go ahead and calculate this. So we get 1.8 minus 0.135 times 10,000 ohms. And we get our VD is equal to 0.45 volts. And so our VDS value is 0.45 volts. And we need to compare that to our VGS minus VTH. Okay, so our VGS value is 0.9 volts minus our VTH, which is 0.6 volts, which is 0.3 volts. And we can see that 0.45, which is our VDS value, is greater than 0.3. And therefore, we are in the active region. However, we are being asked to find the drain current. Luckily for us, we just did that calculation right here. So our answer to part C is 0.135 milliamps. Okay, lastly, let's move on to part D. Okay, let me go ahead and erase this real quick. Okay, part D is asking us to find the maximum allowable value of VDD such that M1 is in the cutoff region. Okay, so this is basically saying we are right in between the cutoff and the triode region of activation. So what that means is our VGS has to be equal to VTH. Let me go ahead and write this. VGS is equal to VTH. And I was able to make that conclusion because we are wanting our VGS value to be the max it can be. And so we want it to be equal to VTH because that will be the largest it can be in the cutoff region. So our VTH is 0.6, therefore our VGS value will also be 0.6. Now remember, we were trying to find VDD, and the relationship between VDD and VGS is shown right here, which is VDD is 2 times VG, or VGS. And so our VDD value, is going to be equal to 2 times VGS, which is equal to 1.2 volts. And this concludes part D of our problem and problem 1 of the fall 2021 final exam. Okay, for this next problem, we are trying to find the current ID1 and the value of W over L. So, in order to find ID1 for part A, we first need to determine the region of operation, like we have done previously. And so, this means we need to find our VGS value to first figure out if we are in the cutoff region. Now, it is important to note about these transistors is that there is only one current going from source to ground. We'll call it ID. And that is because there's zero current going into the gates. IG is equal to 0, and that's for all MOSFETs in DC. And so that means that the drain current is equal to the source current. Okay, so then, and on top of that, our NMOS mu-naught COX value are the same for both transistors. Our VTH value is the same, and our W over L value is the same. And so this means that our VGS values have to be the same for both transistors. So if you look at transistor M2, we can see that the gate current is 3 volts and the source current is 0 volts. So that means that VGS has to be 3 volts, which is larger than VTH of 0.65. So we are not in the cutoff or the edge of cutoff region. Now we have to figure out what our VDS value is to see if we are in saturation. So our VDS values will also be the same for both transistors, right? Both transistors are functionally the same, so they have to have the same voltage drop across each of them. So we are trying to find the potential difference from the drain voltage of M2 to the source voltage, which is 0. So this point right here, we'll call it VDS2. One way to figure out our VDS value is by realizing that both these transistors are the same, and there's going to be the same voltage drop across each of them. And so this VDS value is going to be half of what the supply voltage is, and therefore it's 4.5 volts. And 4.5 is larger than VGS minus VTH, which is 3 minus 0.65, which means we are in the saturation region. And so to find ID, or ID1, we use the equation 1 over 2 mu n COX W over L VGS minus VT squared. And now we just plug in our values. Our VGS is 3 volts, our VT is 0.65 volts, our W over L is 7 over 2, and our mu n COX is 0.11 milliamps per volt squared. Okay, let's see what that is equal to. 3 minus 0.65 squared times 7 over 2 times 0.11 divided by 2. We get 1.063 milliamps. Moving on to B, and here I'll do this in a different color. B is asking us to find a new value of W over L such that transistor 2 is biased at the edge of saturation. So we're trying to find a new value of W over L for transistor 2 to make it at the edge of saturation, right? So edge of saturation is right here. So VDS is equal to VGS minus VTH. And we're going to use this saturation equation. So it is a given that VDS is equal to VGS minus VTH. And more specifically, we know that VDS2 is equal to VGS2 minus VTH. So we know that VGS2 is 3. We know that VTH is 0.65. So 3 minus 0.65 gives us our VDS value of 2.35 volts. Okay, so that is what this point voltage is right here. And so that means that the voltage drop across M1, so VDS1 is equal to 9 minus 2.35 volts, which is 6.65 volts. Okay, and then we are making the assumption that our W over L value for M1 is still 7 over 2, as that is not changed. We're trying to find the W over L value for M2. So this means that we have everything we need to solve for our current, ID1, because that is equal to 1 over 2. Our mu in COX is 0.11. Our W over L is 7 over 2. Our VDS1 is 6.65 volts minus our VTH of 0.65. And then we square that. All right, 6 squared, 36 times 7 divided by 2 times 0.11 divided by 2. And we get our ID current is 6.93 milliamps. Okay, this means that the current going through M2 is 6.93 milliamps. So then we can use the same equation to solve for ID2. However, we just changed the voltage. So we know our ID1 to be 6.93 milliamps, which is equal to 1 over 2. Our mu and COX is still 0.11. However, we are trying to solve for W over L. And in this case, our VGS voltage is 3 volts, right? The voltage drop across from the gate to the source is 3 volts, minus 0.65 squared. And now you can algebraically manipulate this to solve for W over L, and that W over L is equal to, let's just divide everything over onto the other side. So you get 6.93 divided by 1 over 2 times 0.11 times 3 minus 0.65 squared. Okay, let's find out what this value is. So 3 minus 0.65 squared times 0.11 divided by 2. So let me copy that, and we'll take 6.93 divided by our previous answer, and we get 22.8157. So our W over L is equal to 22.8157. So for part C, we're finding the current ID1 just like we were in part A. However, the circuit is a little bit different. So looking at it right here, we have a M2 is a PMOS transistor, M1 is an NMOS. And so how does it change when we're dealing with a PMOS transistor? Well, there will still be just one current, ID, right here. And one thing to note is that this is our source now for the PMOS, and this is our gate. And that means that our VGS, and it's important to note that whenever we're referring to VGS, we do the absolute value of it. That is equal to 3 volts, right? Because there's a 3 volt difference between the gate and the source in this case. Okay, and then 3 volts is greater than VTH, so which is greater than VTH of negative 0.65 volts. Okay, and then one thing to note, this value is actually negative, but that's because our gate and source are flipped in this case. So there's a higher potential at the source than there is at the gate. That's why that's negative. But we get away with just comparing the absolute values of both. So 3 volts is greater than our VT, which is 0.65 volts. Okay, so we know we are not in the cutoff or the edge of cutoff region. So next, let's assume we are in the saturation region. And if our equations work out, then that means we really are in the saturation region. If it doesn't, then that means that one or both of our transistors are in the triode region. So let's take the equation ID is equal to 1 over 2 mu n COX W over L VGS minus VT squared. And this is ID 1. However, our mu n COX for the PMOS transistor is 0.04 milliamps per volt squared. Our VGS for the PMOS transistor we know to be 3 volts. Our VT is 0.65, and our W over L is 7 divided by 2. So let's go ahead and calculate that real quick. So 3 minus 0.65 squared times 7 divided by 2 times our 0.04 milliamps per volt squared, and we end up with 0.387 milliamps. 0.387 milliamps. Okay, so that's our part C. Okay, and I'll do letter D in purple. So again, we're trying to find the new W over L such that transistor M2 is biased at the edge of saturation. And so what this means, again, VDS is equal to VGS minus VTH. And we know our VGS for transistor M2 is 3 and VTH is 0.65. So that means our VGS value, again, is 2.35 volts. Now this is very similar to the last problem, except the transistors are flipped. So this is VDS for M2. Our VDS of 1, right? So if the voltage drop across M2 is 2.35 volts, VDS 1 has to be 9 minus the voltage drop across the transistor, 2.35 volts, which again is 6.65 volts. Okay, let's plug this into our ID equation. So let's plug in the M1 values to solve for ID, just like we did in part B. So we know that ID is going to be equal to 1 over 2 times our mu naught COX for the NMOS transistor, M1, is 0.11, times W over L, which is 7 divided by 2, times our VGS value actually is 6.65 minus 0.65 squared. And as you can see, we actually used all the exact same values from up here because these problems are very similar. And so we actually get our ID is just equal to 6.93 milliamps, like we did before. Okay, and then for the final step, just like how we did in part B, we have to plug in our current and solve for the new value of W over L so that M2 is biased at the edge of saturation. And so the only thing that changes in our part D for this problem is actually our mu naught COX value, which changes because we are using a PMOS transistor for M2. So it changes from 0.11 to 0.04. So let me go ahead and write that. W divided by L is equal to 6.93 divided by 1 over 2, 0.04 now, times 3 minus 0.65 squared. And let me go ahead and calculate this value. So 3 minus 0.65 squared times 0.04 divided by 2. And we're going to take 6.93 divided by that number to get 62.74. 62.74. And this concludes Part D of Problem 1 for the Fall 2018 final exam. And this also concludes today's review session for MOSFET DC Analysis circuits. Thank you for watching.